Okay, so I want to start here. It used to be that I would have to read a journal article or actually crack open a textbook about environmental science in order to see the rationale for my work, displayed. But I woke up one morning and I saw CBS morning show, and they were talking about the dead zone. And then a couple weeks later, I was in my vehicle on the way to Purdue, and I was listening to NPR, and I heard about the dead zone. I'm thinking, wow, this is just on front cover. There's nowhere to hide. And that leads me to say we really have to be serious about nutrient loss reduction. And so the epoxy task force mandated that 13 states in the Midwestern Corn Belt that feeds the Mississippi Atchafalaya River Basin has to develop a nutrient loss reduction strategy, okay? And so one of the goals of the strategy is by 2025 is to reduce the nitrate and nitrogen load by 15% that's coming to the Gulf of Mexico to reduce hypoxia. But then I thought about that and said, in order to get this reduction to actually occur, we need to be able to address all nutrient management strategies, especially that deals with corn. We can't think, well, we're only going to address all of those that apply most of the nitrogen in the spring. And we're just going to forget about the guys that have manure that goes down in the fall, that has DAP that goes down in the fall, and that has anhydrous that goes down in the fall. We have to address all, because when you look at the strategies, cover crops were selected as one of the most effective adaptive management practices, but it's unique because it's able to cover all acreage. So my job is to talk about what's the function of cover crops in the landscape and how do they help nutrients get conserved, then how do they help nitrogen cycling occur. And we're going to focus on nitrogen management that's linked to corn, okay, corn production. And so when you think about the cover crop, the first thing that happens once you get a good stand is that you have nitrogen conservation. In other words, the cover crop interacts with the inorganic nitrogen pool. And that pool could be made up of residual nitrogen from the previous cash crop, if you're in a corn-on-corn situation. It could be made up of manure nitrogen that is releasing and becoming available in solution. And it also, if you're in a high organic matter system, even in a low organic matter system, you're going to have nitrogen that's mineralized, and that cover crop is able to absorb or interact with that nitrogen. And then second, the focus is, I do a lot of talks to farmers, and they want to know that they're happy to see that cover crops can take up nitrogen, can conserve nitrogen, but then they want to know when is that nitrogen is going to be released. And so Stephen Mirsky is going to talk about that later on. And then we want to track that nitrogen after it's released into the plant, whether corn or soybean, and we want to understand if the presence of that cover crop cycling and scavenging nitrogen is affecting the uptake and the yield. So that's what we're going to focus on. I'm going to use two data sets, one on a field scale and one on a watershed scale, to kind of demonstrate what we've seen thus far. So the first is we're looking at basically two of the nutrient loss reduction strategy adaptive management plans, and the first is to move nitrogen from the fall to the spring. Okay, when you look across all of the science assessments and nutrient loss reduction strategies, you basically see that should account for about 10% reduction in what you're seeing leaving the tile as far as nitrate and nitrogen. The second is to be a little bit more aggressive, and there's a lot of work that have been done in Iowa and so forth on the second one, is to move the nitrogen from fall to spring and then augment the system with cover crops, okay? And you should get a further reduction somewhere to like 30% or so, okay, from 15. And then the third is one that we developed and evaluated in central Illinois quite a bit. And that is, in central Illinois, those of you that are from Illinois, you know, or north of Illinois, you know that there's a significant portion of the nitrogen that's purchased by farmers is applied in the fall. Okay, so we're not allocating that. I mean, we're not recommending that that happen, but we do understand that it does happen. And so if we're going to get that 15% reduction by 2025, we have to do something with those systems also. So what we decided was to have farmers inject anhydrous into a living stand of cover crops. And early on, we saw a pretty good response. So we wanted to test that over a system where we can measure the water and understand how it's affecting the concentration in the tile. So to do that, to analyze those 3 scenarios, we have 5 treatments. The first one is the zero control, no fertilizer, no cover crops, just corn and soybean growing. The next 2 is basically you have the dominant portion of the nitrogen applied in the spring versus the fall, and with or without cover crops. And then 4 and 5 is that the dominant portion of the nitrogen is applied in the fall, 70% with and without cover crops. And the total amount of nitrogen applied is right within the range of the MRTN, 224 kilograms per hectare. That's about 200 pounds per hectare. The cover crops that we're using is a mixture of cereal rye and radish, where cereal rye is dominant. And so this is what that field looks like, 15 individually tile drained fields. The tile laterals are about 45 feet apart. They converge 15 feet or so before those yellow dots. And that yellow dot is a tile monitoring station where we can tap right into the tile water and measure exactly the impact of the surface management practice on the tile water. This field is a strip till before corn, no till before soybean field, and it was that way about 8 to 10 years before we got there. So this farmer was already progressive, okay? And so this is a good slide to demonstrate that we're not just hand cranking the cover crops out, in the field. We don't have a robot going between each row, one row at a time. We actually have farming equipment that's going through standing corn and dropping cover crops at the base of the plant at a significant speed, and was able to knock down less than 1% of the stand. So the farmer was pleased, so I was pleased. So let's look at the biomass, and this is above ground shoot biomass. And so the takeaways here from this slide is, number one, we didn't get a difference or effect of nitrogen application timing on the cover crop biomass. Okay, so in each year we had 2014, 15, 15, 16, 16, 17, when we had the greatest biomass in 17. And if you look at 2015, you can see significant growth in the fall. That's because we didn't really have a fall. It didn't really get cold. And so, but the years where it got cold, like it's supposed to, you have significantly more growth of that cover crop mixture in the spring versus in the fall. Okay, and the average biomass is about 1,300 kilograms per hectare. In uptake, above ground in uptake was about the same trend. Okay, where you actually had winter conditions. You got significantly more spring growth, and we averaged about 66 kilograms per hectare of nitrogen being taken up. And if you think about it, that's about 30% of the equivalent weight of what the farmer applied. So over a 3-year period, the cover crops have the capacity to interact with about 30% of the average in application for corn in that region. So this is a doozy. So this is the nitrogen load over 2.5 years, so the lifespan of the study. And this is cumulative over time, and that blue line is the precipitation that's cumulative over time. And so we had a total of about 63 inches of rain, an annual average of about 25 inches per year. And when you look at and try to discern differences between the treatments and loading, what we saw was that the fall nitrogen-dominated system without cover crops yielded about 52 kilograms per hectare per year in that system. And then when you add cover crops, you reduce that by 42%. Okay, the spring nitrogen without cover crops yielded about 60 kilograms per hectare per year. And when you add cover crops to that system, you reduce it by 50%. When you compare fall versus spring, it was about equal. Okay, it was a wash. That's very common in the literature in the Midwest, where you don't really see that 15%. It's not guaranteed. It's dependent on the weather, soil temperatures, which drives mineralization and microbial activity. Next, when you look at fall with no cover crop versus spring with cover crops. So if a farmer was to decide to move the nitrogen application from the fall to the spring and then add cover crops to the system, then that yielded a 42% reduction in nitrogen leaving the tile, leaving the system through tile. Then when you look at, this is very interesting, spring without cover crop versus fall with cover crops, there's a 50% reduction in the nitrate leaving the field. So this farmer one farmer decided to move the nitrogen from fall to spring. The other farmer said, you know what, I'm just going to use cover crops to try to mitigate my losses and leave the nitrogen in the fall, and there was a 50% reduction, okay? And so the overall message here from this slide is that despite the nitrogen application timing, cover crops was able to make a 42 to 50% reduction in nitrate leaving the field, which I thought was pretty significant. And this is just flow weighted concentration. So when you look at this graph, it's flow dependent. This graph is not flow dependent. So we normalized all of the numbers by flow. And you can still see in 2015, that soybean year, where the green bars, the cover crop treatments, and also in 16, it's more exaggerated. You can see reductions from the cover crop. So that just echoes what we saw in the previous slide. So one of the things that we did was to try to figure out, what are the cover crops doing? Are they actually cycling nitrogen? And what we found was a 2-to-1 ratio. So a 2-to-1 ratio between the nitrogen in the cover crop biomass versus the nitrogen that the cover crops did not allow to get to the tile drainage. I'm gonna say that again. So 2-to-1 ratio of nitrogen that's in the cover crop biomass just above ground in the shoots versus the nitrogen that the cover crops did not allow, that prevented from reaching the tile. And so we were trying to figure out a hypothesis on what's happening there, and I'm not the only one seeing that throughout the literature in the Midwest where you have cover crops and tile drainage. Authors and scientists are seeing the same thing. And so what we think is that it's possible that all of the inorganic nitrogen pool in the soil over the fallow period is not going to reach the tile. And it's not going to leave the field. That's impossible, right? And so what's happening is that possibly the cover crops is tapping into that larger pool of inorganic nitrogen that's not susceptible to being lost, that's less susceptible to being lost by tile drainage, and is also tapping into or interacting with nitrogen at the lower portions of the soil profile that is more susceptible. And so when you add up those two interactions, it's coming up to 2 times the amount that it prevented from leaving the field. One could also say that, hey, maybe you're not totally measuring everything that leaves the field. Maybe nitrogen is going below the tile drainage so that that portion that's leaving the field is larger. That is also possible. So here's the money slide, right? This is not pretty, fellas. This is not pretty, gals, okay? Our corn years were 2015, 2017, so the odd years. We did see reductions in yield where we had that dominant cereal rye mixture coming before corn, okay? What we're doing to offset that is that this slide basically sprouted out a different line of research that we're starting in our lab, where we're going to try to optimize starter nitrogen rates for corn that's following cereal rye. And so we followed all of the rules here except putting cereal rye before corn. We terminated 3 weeks before planting. That was pretty aggressive, which yielded a C/N ratio of 10 to 17, so we weren't anywhere close to the 21 to 24 to 1 ratio that we see in the textbooks and hear on the radio and read in Prairie Farmer. So the only thing that I can see here is that the cover crop, the SARE was releasing nitrogen slower than what we actually thought. And when you have, in 2017, the rain shut off after June, you don't get a chance to catch up, and so you have drastic yield reduction. So we think that we have a good baseline here where we have yield reductions, and we're going to change the nitrogen management, not to add more, but to add a larger portion at planting with 2x2 applications, and to see how that affects yield. And then we want to see how is that affecting the spring nitrate losses. Soybeans is a good story. No difference in soybeans. So we don't have a greater yield, but we didn't take a yield cut. So the next scale is the watershed scale. So we got really ambitious. So we looked at these practices on a plot scale, then on a field scale, and we said, let's see what happens on a watershed scale. We can get farmers to mass adopt cover crops across a pretty large watershed. Can we see a signal in the water? Okay? And so one thing you know about plot scale research, you can control everything. You can control the rate of nitrogen when you apply the nitrogen, if you're going to grow corn, if you're going to grow soybeans, whether you want to do controlled drainage or what, you control everything. But on a watershed scale, you have no control. You're working and you're a guest of someone else. You're on their land and they're the boss. So you have to reduce your experimental control, and you have to rely heavily on the farmer to allow you to execute your science. And you have to actually get input. And I found that their input is really, really good, okay? And so we wanted to test this cover crop idea, this technology, in an uncontrolled environment. So we located 2 watersheds within the Lake Bloomington watershed, and if you're not familiar, Lake Bloomington serves as the source of water for the town of Towanda and the city of Bloomington. And so we found a larger watershed, which is about 465 hectares, and we found a controlled watershed, about 262 hectares. In that larger watershed, we tried to cover crop 50% of that watershed. And you can see 93% row crop agriculture, about the tile densities at about 90% of the land area, poorly drained, silty clay loam soil, somewhat poorly drained, okay? Less than 2% slope most of the time. Typical central Illinois or central Midwestern watershed. And so the smaller watershed consisted of about 4 farmers that I'm working with, and then the larger watershed is about 6 farmers, okay? Sorry, 10 minutes, great. So the objectives were simple. We wanted to see, how does this cover crop grow across this watershed, and what's the variation in uptake? We want to compare cover crop growth and uptake on a watershed scale versus the field or plot scale. And we wanted to see if we can find an impact on water quality if we mass adopt cover crops, so 50% of that watershed. We took water samples at the outlets of each one of those watersheds to measure nitrates and phosphate, but we're just going to focus on nitrate. We flew on the cover crops each fall from late August to mid-September, so we were on time. And basically all of the farmers selected the same cover crop, and they wanted to rotate the cover crop before the cash crop. So they wanted to go SARE radish that gives you a higher seeding ratio before soybeans, very smart. And then they wanted to go radish oats or annual radish before corn. Okay, so they already knew that. So this is just a shot and just shows you that in the even years it's dominated by soybeans, and in that year you can get 53 to 100% of the land area to be fall applied. So here's our biomass, and the story here is that SARE radish versus radish oats was more dominant for biomass and in uptake. And then the next year, one of the farmers decided, I told you I had no control, he said, hey, I want to do annual rye instead. So and he had 360 acres of the 500 acres of cover crops. And so what did I say? Sure, anything you want to do. And so you can see that even with the annual rye, SARE rad combination, the mixture was significantly greater in both biomass and in uptake. So I had one of my PhD students use SAVI, remote sensing, to create a 30-meter resolution map so that we can get standard deviations across that 500 acres of cover crops. And you can see the variation there, and this is a SARE rye field. And then at the bottom, you can see the means of the watershed scale versus the plot scale, pretty close. But when you look at the variation, which is the percent coefficient of variation, it's pretty wide variability you find on a watershed scale versus a plot scale, okay? And we saw that same trend in both years. Now, this brings us to, what's the impact of the in-uptake and the growth of cover crops on 50% of the acreage of 1,100 acre watershed? Did we see an impact? And so the red boxes represent the cover crop seasons, and the orange dots represents the tile water at the outlet of the control watershed, and the blue line represents the concentrations, flow-weighted nitrogen concentrations at the outlet of the cover crop watershed. And so if you focus on the second two cover crop growing seasons, you can see that there's possibly a signal there where the blue line is more likely to have a lower concentration compared to orange. The orange dots of the control watershed, and then they are more similar when you're not in a cover crop growing season. And so we think that there could be something there, definitely if we were to increase the inclusion rate and adoption across that watershed. But what we want to do is to go another 3 years here and to see if we can see the same patterns and to see if that pattern increases and become more prevalent to us. And then at the end, what we're going to do is in the control watershed, we have a really good baseline now. We would have 6 years of baseline. So we want to then cover crop 50% of the control watershed to see if we can see a signal and have a very, very good comparison to no cover crops being in that watershed and having water data, water quality data for 6 years. So as I sum up, on a plot scale, on average, the cover crops were able to interact with about 30% of the nitrogen fertilizer applied by the farmers in that region. There's about a 2-to-1 ratio of cover crop shoot biomass in compared to the nitrogen that did not leave the field, so there's some cycling potential there. Thirdly, cover crops reduce nitrogen loading by 42 to 50% despite when the nitrogen was applied. I think that's the big take home there. And we did have a reduction in yield as far as corn, where you have SARE radish, but no effect on soybeans, and we're going to work on that with optimizing starter rates. On a watershed scale, it's possible to mass adopt cover crops in a watershed if you can get farmers and producers and owners to work together and have some money to help cost share. The radish SARE mixture, the uptake across scales was similar, but when you look at the variation, the variation is wider when you're on a watershed scale versus the plot scale, and there was a general signal that there's a potential for water quality impacts when you cover crop only 50% of the larger watershed on a watershed scale. Thank you.